So now we have two settings on our camera that we can modify when we want to take a photo that is properly exposed and maybe give it some sort of exposure effect. So maybe we want to have a longer shutter speed and get some motion blur. Maybe we want to decrease the ISO and clean up the noise a little bit, or make the image a little bit cleaner. But there's actually a third setting that we have control over as well. And this is called the aperture of the lens. And so basically, as we've learned about shutter speed and ISO, we've been figuring out different ways that we can allow photons to enter into the camera and be basically counted by the camera when showing us an image. And so aperture is yet another way to do that. So whereas the shutter speed is actually an amount of time, this actually physically blocks or physically allows a certain amount of photons or certain amount of light to enter into the camera. And so the whole reason that I show you basically an icon of a lens is that the lens is responsible, in almost all cases, for changing the aperture and therefore changing the amount of light that is allowed into that particular camera. So inside of the lens, and very much like our pupil lets in light. So if you think about the eye for just a moment, we have the pupil that lets in light, and we have the iris that, when it's dark, it gets a little bit bigger to let in more light, and when it's bright outside, it contracts or it gets smaller to let in less light. And this is exactly what we were talking about when we were referring to aperture. So there is actually the concept of an aperture for your eye, where the aperture is really just the hole, basically the size of the hole that allows in the light. So just like our eye, our cameras have an aperture as well. So there's an iris of some type that's either metal or plastic, and it usually closes down on the lens or inside of the lens so that less light is allowed to enter into the lens and therefore allowed to go to the back of the camera. And so this is sometimes difficult to notice, but if you have an SLR especially, and it's especially useful if you have it with you today, though you don't need to, one of the things is that SLRs have what's called a depth of field preview button. And one of the things that this button lets you do is that when you click it, there's this sort of noise. I don't know if you can hear it, but it's very faint. But what happens is that it actually closes the aperture in the lens, and you can actually see how big the aperture is. So if you're looking towards the front, you can actually see it. But if you're looking through the actual camera itself, you're not going to see it. It's not going to look smaller. It's just going to change how the picture looks. And we'll talk about that in just a little bit. And so I trust you guys, but I'm going to pass this around and allow you to push the depth of field button. And every year, I always get the camera back, and I expect to again this year. But every year, I always get some pretty funny photos on here from people accidentally pushing the shutter button, and I am not. It's not beneath me to post them. So be careful. So anyway, when you get the camera, there's and you'll notice that it's shaped like an SLR, obviously. But to the left of the lens, there are a couple of buttons, and at the bottom of the lens, right here, there's a little button. And if you push this button, that's the depth of field preview button. And so if you just hold the camera and push that button, then as you're looking into the lens, you'll see this diaphragm actually close the aperture itself. Now, if it stops working, it's probably because the camera has turned off just automatically. So just flip the switch back here from down to off and then just back up to on, and then you should be able to push the aperture again. Okay? All right, so I'll just pass it here and then so for you guys to take a look at this. So as I continue talking about this, but aperture, this one is a little bit more complicated. So whereas in shutter speed and ISO, we could very neatly, very nicely double or halve the numbers in order to figure out how many additional stops or how many fewer stops of light we have to work with. Aperture is actually a bit different. So usually you'll see numbers like 1.4 to 2 to 2.8 to 4 to 5.6, so on and so forth. And this just sounds really messy. But if we think about why this happens, we realize that there's a very legitimate, very real reason why these numbers are so complex. So the aperture is denoted by what's called an F number. And so normally these numbers that I just spewed at you, 1.4, 4, 5.6, these are actually F numbers. And the F number is just a ratio. And now, so in the long run, what's most important to get out of this is that you understand what this F number is and what the aperture is and what it does for your camera. But what I'm trying to do today is explain to you why these numbers are as crazy as they are and give you a way to understand them and make them a little bit more tangible so that it makes as much sense, hopefully, as the shutter speed and as the ISO. So the first thing to that end that you have to realize for the F number is that it is just a ratio. So we have a focal length, which basically describes how zoomed in the lens is, and we'll talk more about this in the optics lecture. But the longer focal length you have, it's basically, this is a 200 millimeter lens versus what's on the camera right now is a 50 millimeter lens. So it's generally a longer lens as well, and it's more zoomed in. So you have to take this focal length and divide it by the diameter of the lens. And so realize that what you are seeing here is, of course, an oversimplification of a lens. So there's, as I showed you in the first lecture, a lens is actually a complex mixture of glass elements where there's not just one piece of glass, there's many glass elements that are combined and sorted in different ways so that to bend the light, so to speak, onto your sensor and produce the final image. But there is a glass element in there that's sort of the limiting factor, and so this is the limiting factor that you can think of as being this diameter here. So you take the focal length, you divide it by the diameter, and you get basically this F number. Now what's important is that, remember that I said that doubling or halving the number of photons will double or halve the brightness respectively. So that can happen through a number of ways. That either means that we can double or halve the shutter speed, which actually means that if you have the shutter open for twice as long, you let in twice as many photons. Or in this case, when light is sort of entering in through a lens, you can double or halve the area itself of that lens. So if you double the area, then you were letting in twice as much light. If you halve the area, you were letting in half as much light. And now the problem here is that you'll notice the F number isn't a function of that area. It deals with the diameter. And so if you remember your geometry, the area of a circle, is pi r squared, or half the diameter squared. And so you have this complex thing where in order to figure out the area, you actually have to have this diameter and square and multiply times, and it gets to be quite a mess. And actually, I'm not going to worry you with showing you a lot of this math right now, but I do have a very nice handout that I wrote, I don't know if it was a couple years ago or what, and in this document I do show you actually all of the math that goes behind this number, and so you can actually see where we get these numbers from and how they are derived and why this makes a difference. Why doubling, well, obviously doubling the area will increase twice as many photons, but if we take that into account and if we consider the diameter as being part of the F number, then how we get these sort of crazy numbers that are output by it. But there's a couple of really important things to remember about the F number, and that is that basically what you can do, all right, let's see, I'm going to do this differently than I expected, just because I think this will be a little bit clearer. But when you're trying to remember an F number, or the F numbers that exist for a camera, you will generally see crazy numbers, like I said, of 1.0, 1.4, 2, 2.8, 4, 5.6. You may say, well, how on earth have you memorized all these? It actually sounds kind of crazy, but there's actually a very good pattern to this. So each of these numbers represents a one-stop difference in the F numbers. That means that if I've gone from an F number of 22 to an F number of 16, then I've actually doubled this ratio, or I've doubled the area, so I'm letting in twice as many photons. So this is a change of one stop between each of these numbers. But there's a very easy way to remember this, and that is to memorize these first two numbers, 1.0 and 1.4. Just remember those. And then double each one. So you double the first one first. 1.0 times 2 is 2. Then you double the next one next. 1.4 times 2 is 2.8. And you just keep going. 2 times 2 is 4. 2.8 times 2 is 5.6. 4 times 2 is 8. 5.6 times 2, and then they round a little bit. It's about 11, so on and so forth. And you can get to this really big, fancy number. And so one of, or not necessarily big, fancy number, but generally these are the numbers within the range that you will generally play with when you're talking about a camera. Because one-stop difference, remember, is quite a large change in the amount of light. So if we're doubling or halving the amount of light here, if we do this, 1, 2, 3, 4, 5, 6, 7, 8, 9 times, that's 512 times more light from the lowest F number, F1, to the highest here. So that's quite a big change. And so there's a lot that goes into this F number, and obviously it relates very strongly to the lens itself. So all of these lenses have different aperture ratings, and they can have different large apertures or smaller apertures, and it really varies a lot. And we'll talk about some of that stuff a little bit later. But what's most important to realize is that the lower F numbers, so besides having remembered this trick where you memorize those two, 1.0 and 1.4, and doubling them will give you this line of F numbers. But what's most important to remember is that the lower the F number, the brighter the image. So one of the things that this document is actually going to show you, and I don't want to waste your time going over it on the blackboard directly, because it can get it just turns into a math lecture basically, is that the very back page actually shows you calculations where we calculated the F number, or the aperture, of the pinhole photo. So if you remember from the first lecture, we had this, the camera was set on top of here, and there was a very small hole at the end of a body cap, basically, that let in a certain amount of light. And that is a restriction of aperture, because now this aperture is very, very small, especially when compared to the smallest aperture that you'll see on the camera as it goes around. And we were curious to know what the F number was, because the lens that's on the camera right now is capable of an F number of 2. So F2, and that's pretty respectable. Normally you'll see like F4, F5.6, but we wanted to see what it was, and I don't really remember. But we found out that it was actually an F number of 128. So this is actually a very, very small aperture, and we figured out through that even further. We were able to measure about how large the diameter was itself. So we figured that it was about 0.4 millimeters large, the size of that pinhole, just by knowing some of this relatively simple geometry of knowing the area of a circle is pi r squared, and by knowing this ratio, that the F number is the focal length divided by the diameter. And in fact, if you remember from the first lecture, I gave you a little bit of information, or I gave you just a little factoid, and I said, put this in the back of your mind. It's going to be important for us later on, and that was this symbol right here, this circle with the line through it. And it is very important now, and especially so when calculating the focal length of the pinhole camera, because this represents, if you remember, what does it do? The position of the lens. So the position, not of the lens, but the position of something else. Right, the sensor. It's the focal plane. So where that line goes through the camera, basically, that's where the sensor is, in space. It's where that position is. And so by measuring where the hole on the pinhole camera was versus where the sensor was, we were able to determine the focal length of it. And so by knowing the F number and by knowing the focal length, we could then figure out the diameter pretty easily just by dividing a couple of numbers. So yeah, I get excited about this stuff. I wasn't, an MIT geek, so this stuff excites me a lot. And that's why I'm trying very hard not to, go crazy on the board with all of this math. But all of this stuff is actually pretty interesting, and we'll pass out this document at the break, which is coming up pretty soon. Actually, now it seems like a perfect time to do it. So why don't we take a 5-minute break, and you guys can wet your whistles with some of this information here. All right, hello everyone, welcome back. So as you can see, we've passed out these documents now, and they'll also be available online and on the course website tonight for you to follow along. But you'll notice that rather than me just talking at you, I think it helps to actually look at some of this stuff concretely. And so, for example, I spent probably longer than I should have making sure that these two circles on page 2 were actually twice the area of one the other. But now you can actually see relatively the size of like what doubling the aperture actually means to scale. So A1 in this case is actually twice as large as A2, even though it may not look it, it is by area. And so this is one of the reasons why this number is so complicated. And if you follow along in the math, hopefully it will make a little bit of sense about where these numbers have come from. But as I mentioned, in the end, what's really useful to remember, you don't have to remember the jargon or even the steps that are necessary to calculate this or to derive this from scratch. It's really just meant to give you sort of an intuitive feel or a more intuitive feel from where these crazy numbers come from. But in the end, you can just memorize that simple rule that I mentioned of memorizing 1.0 and 1.4, doubling each. And that is shown to you at the bottom of page 3 for you to be able to follow along. And so just like with shutter speed and ISO sensitivity, when we're changing the F number, we actually are modifying the way the image is going to look. And this is more than just changing how much light is actually entering into it. There's actually a very real impact on the photograph itself by changing the aperture, and that is the background blur. You might hear this in a couple of different ways. You might hear background blur or depth of fields or incorrectly referred to as bokeh, and we'll talk about some of these things a little bit later. But basically, when you have one lens and you have it set at a specific focal length and you decrease the F number, so you're making the aperture larger, remember, so you're making the aperture itself larger, so you're letting in more light, and you're decreasing as a result the F number from, say, 5.6 to 4 to 2.8 to 2, so on and so forth. What you are doing is you are isolating the foreground, or whatever you have focused on. You're isolating it more from the background. So if you want, a very smooth, very very nice blurry background that you want to use to isolate the foreground, you want to use, among other things, a very, very low F number. You want to go pretty much as low as you possibly can that's possible for your specific lens. And so remember that I mentioned that the F number is just a ratio. It's just the focal length divided by the diameter. And the diameter of a lens is very real. It's very fixed, and I cannot make the diameter any larger than this. So this lens has a maximum rating, has a maximum aperture rating, or it has, basically an F number that's printed on it that tells you the lowest F number that it can possibly go to. So if you have a lens that is capable of a somewhat low F number, then what you will get is a very nice background blur such as this. And so generally with these things, or generally with background blur, you can get it through a variety of means. It's not just through modifying the aperture, modifying the F number, though that is one way. Another way to do it is you could have a bigger sensor. Having a bigger sensor, you will generally, for the same F number, have a much shallower depth of field. So in other words, as you get bigger in sensor, you will have a blurrier background, all other things remaining the same, though that is it's a little bit of a myth, and we'll talk about why in a future lecture, of course, but a bigger sensor is just, that's one of the results of it. And so another thing is that if you have a longer lens, so if you have a more zoomed in lens, in other words, if you have one that's, sort of obnoxiously long like this, you will generally get more background blur than you would in a lens that's more wide, that has, much more of the scene within it. So conversely, if you want to take a photo that has quite a lot in focus, so not only the foreground but also the background, that means you need to use a relatively high F number, but you also might want to use a relatively low, relatively wide angle lens, or you may want to use a smaller sensor such as is found in compact cameras. And so if you have been using a compact camera for a long time and haven't really used an SLR, and you've always sort of looked at photos and said, man, how do they get this sort of background blur out of them? It really doesn't matter how much you lower the f number on those, you have physics working against you, frankly, and the size of the camera is really limiting the size of the aperture itself. And so that, as a result, then gives you a much longer depth of field, a much larger depth of field, which means that you get more of the scene in it. And so there is actually another way that we can get longer depth of field, and that's using what's called a hyperfocal distance. And we'll talk about that, of course. And like I said early on, there's a lot of stuff where I have to tease it, because if we go over it all, then there's no way we'll get through everything that we need to get through today. But using the hyperfocal distance, even if you are using an SLR, you can try to extend your depth of field as much as possible. And the depth of field refers to the depth of field that is basically in focus. So the larger the depth of field that you have, the more things in focus that you will have as well. And if you have an SLR camera and you get a lens such as the Nifty 50 that's on the camera that hopefully somebody still has around here, one of the things you'll notice when you use some of the lower f numbers is that the depth of field can literally be inches or less on some of these cameras and some of these lens combinations, depending on what you're using. And so it can become really quite a pain when you could just focus on anything and everything would be in focus with a compact digital camera. Then it really becomes an issue of making sure you get the focus absolutely correct. And so there's, well, okay, I'm getting off into a tangent, but this is one of the reasons this is both a pro and a con when we're talking about SLRs. Now, one of the things about using a smaller aperture or an f number of higher than about f11 or f16 on an SLR, or maybe about f8 on a compact digital camera, is that you actually get an additional physical problem, this physics problem that exists that's called diffraction. And so, while you might think that by putting the absolute highest f number that you possibly can means that you're going to get absolutely everything in absolute sharp focus, you actually have this physics phenomenon called diffraction working against you, where all of a sudden it's going to make everything sort of soft, and it's just going to drive you crazy, because you'll say, hey, Dan told me that everything is supposed to be in focus, but it all looks really fuzzy to me, and it's a different type of fuzzy than being out of focus. It's actually diffraction. So that's just sort of a saving my ass sort of thing, where I know you're all going to go home and try it, and you're going to get mad at me, but there's other things working against you as well. Okay, so we talked about these three ways of modifying values, or modifying these variables, so to speak, on your camera so that you can get exposure to within a certain limit. So you can modify each of these things on your camera to try to achieve a certain effect. So in this case, for example, we wanted a relatively long depth of field. This was using a compact digital camera, so I wasn't using a really large f number, but an f number of about f8. And by decreasing the ISO to 100 and using a long shutter speed, then I was able to get everything in relatively crisp focus. I was able to get a relatively clean image. That means it's not very noisy. And since there's not really much that's moving, I didn't really care that it had a long shutter speed. But obviously, at 10 seconds, you either have to be sitting the camera on the ground and hope that nobody's going to come driving by on this road, or you have to have a tripod with you in order to make sure that you do get an actually sharp photo. But as you noticed, a number of these photos actually have careful consideration placed to all three of these settings. And eventually, this sort of stuff becomes second nature to you, where you're thinking you're in a certain situation and you just you start to learn instinctively what sort of settings you might want to use for that. And you will generally tend to focus on some settings over others. So maybe in the case of sports, for example, maybe one of the things you want to do is increase the ISO a little bit, not a lot, but just a little bit, so you can make sure you get a fast shutter speed. And also, maybe you also want to decrease the f number or make the aperture larger so that you can try to isolate the foreground from the background. And in fact, all of these exposure modes that your camera has on it, so sort of these silly modes that so many cameras have nowadays. It's like a guy running like this, and it's sports mode, and then there's another one where there's a sunrise, and that's landscape, or I can't even remember all of this crap that they put on these cameras. All they're doing is they're just placing certain biases on different exposure values. And now that you understand what all three of these exposure values are, you can replicate all of these stupid person modes okay, I might, regret saying that in the future, but you can replicate all of these for yourself. You can manually set, and you don't even have to manually set all three of these. There's ways that the camera will help you. They have a variety of modes, and I'm getting ahead of myself a little bit here, but they have a variety of modes that will help you choose maybe one of the three or two of the three of these settings, and you can select the rest depending on the situation that you're in or depending on the scenario that you are in. And so long as you remember how each of these impacts the end result, you will actually be able to do exactly what you want to do with the camera itself. So we have these three exposure values. We have shutter speed, sensitivity, and aperture. But there's something that I didn't really mention that perhaps impacts the way the photo looks even more. Does anybody know what that might be? Yes? What was that? So not even the temperature of light, but just the amount of available light, because it's the amount of available light that you have that really dictates how the rest of this is going to go down. So if you don't have a lot of light available to you, then you're going to have to perhaps alter each of these settings in a different way than you would if you had tons and tons and tons of light. So in this room right now, for example, there's not a lot of light, so we would have to restrict ourselves to relatively high ISO, relatively low f number in order to get a shutter speed that's respectable enough to be able to hand hold it. But if we have gobs of light, just tons of light, we're outside and it's very, very bright and we have lots of options, then we can have a very fast shutter speed while having a low ISO, having a slow ISO, and having a relatively high f number. So there is actually a way that you can try to remember when you're outside and you want to take a completely manual photograph, so you're setting all three of these things by yourself, there is actually a rule that will help you determine it, and it's called the sunny 16 rule. And on a bright sunny day, and I'm talking bright and sunny, I mean probably brighter than it was today, and I found that honestly this really works best when you're a little bit farther south than we are up here. But midsummer this will generally work pretty well. On a very bright sunny day, you want a shutter speed of about 1/100th of a second, a sensitivity of about a high ISO 100, and an aperture of f16. So the sunny 16 rule, in other words, means that you set everything to 100, the shutter speed, the ISO, and you just set the aperture to f16. So now let's say that it's slightly overcast, and so now it's maybe 1 or 2 stops darker outside than a completely bright, full sunny day. How can I modify these so that I still get a properly exposed photograph? Yes? Yeah, exactly. So I could move the aperture, I can move the f number down to stopper 2, so maybe rather than f16, I could have f11 or even f8. Anything else that I could do? Yep, I could turn the sensitivity up, so ISO 200 or 400 would work. Or how about the shutter speed? Can I do something there as well? Yep, so I could slow it down. That's right. So I could slow it down so that it's open longer and I capture more light. So maybe I would then have maybe 1/50th of a second or 1/25th of a second. But remember, in that case, each of these things, when you're thinking about this, you're outside and it's a bright sunny day, you have to remember the impact that each of these values have. So if you're outside and you have a relatively long lens, you remember that trick that I told you before where you can generally hand hold something to 1 over the focal length. So if you have a 200 millimeter lens, then you're kind of pushing it with 1/100th of a second, and if you go to 1/50th or 1/25th of a second, then forget it. It's almost guaranteed to be blurry. So what you might want to do then is instead lower the aperture or lower the f number rather by quite a bit, so that you can then maybe keep the same shutter speed or maybe even increase it, make it a little bit faster, so that you could then hand hold that. So in general, you have a bright sunny day, you can use the sunny 16 rule. If it's slightly overcast, you would go down 1 stop to f11. If it's pretty regularly overcast, then you might go down 2 stops. If it's heavily overcast, maybe even 3 stops. Now 3 stops down would be an aperture of f5.6, because from 16, if we go backwards, You can reference the numbers here if you haven't fully memorized all of them, and shame on you if you haven't, right? Because they're so easy. But anyway, if you go from F16, you can see you can count 3 stops downwards. You realize that you go to F11, F8, F5.6. So that's 3 stops away, and that would be for a heavy overcast day.